Integrated rate law. In the last section, we talked about the fact that there are two different types of rate laws, differential and integrated rate law. So let's just review the differential rate law before we move on to the integrated rate law. The differential rate law deals with rate as a function of the reactant concentration. So we had our equation, rate equals K times the concentration of something to the n power. And our integrated rate law deals with how concentration and time are related. So if we have reactions that have just a single reactant, we could say that A decomposes to produce products. And if we wrote the differential rate law for that, we could say that rate equals the change in concentration of A over the change in time, or rate equals K times the concentration of A to the n power, where K is our rate constant and n is the order of the reactant. And remember again that if n equals 1, we say a reactant is first order in the reaction, which means that the change in concentration is directly proportional to the rate. If it's second order for a particular reactant, it means any change in the concentration squared gives us the change in rate. And if we say that a reactant is zero order with respect to a reaction, it means that the concentration does not affect the rate of the reaction. So if we're told that a reaction is first order, and we look at this as a specific example, we've got dinitrogen pentoxide decomposing, and we would write our rate expression as rate equals K times the concentration of dinitrogen pentoxide to the first power, which again, we don't have to write that 1, it's assumed. So this reaction depends on the concentration of nitrogen dioxide. So let's look at a graph. Here we've got the concentration of dinitrogen pentoxide on the x-axis or y-axis, and we've got time on the x-axis. And what we should notice is as the concentration goes down with time going up. Now, scientists like to work with straight lines more than curved lines. So if we use a little bit of calculus, we can convert our differential rate law into our integrated rate law. So now we've got the natural log of the concentration of dinitrogen pentoxide versus time. And we've got a nice straight line. And we know that with straight lines, we can deal with y equals mx plus b, and that'll give us an equation for a first order integrated rate law. So our expression is now going to be the natural log of dinitrogen pentoxide equals negative kt plus the initial, or the natural log of the initial concentration of dinitrogen pentoxide. Notice there's a negative sign in front of K because our slope is going downward, or it's a negative slope. And that means that the concentration of the reactant is a function of time. If we know what the concentration is initially and after a period of time, we can find out how long the reaction has progressed. Or if we know the initial concentration and we know how long the reaction has taken place, we can find out what the final concentration is. So our integrated rate law relates concentrations and time. So in general, if we're looking at a first order reaction, our differential rate law would be rate equals K times the concentration of A, and our integrated rate law would be the natural log of A equals negative KT plus the natural log of the initial concentration of A. And what that shows us is the concentration of A depends on time. If the initial concentration and K are known, we can find A at any new time in the reaction. When we look at the graph, We've got y equals mx plus b that we can apply since it's a straight line. Our y value will be the natural log of a. Our x value will be time. Our m value will give us negative k. And our b value will be the natural log of the initial concentration of A. So anytime we plot the natural log of A versus time, and we get a straight line, that tells us that that particular reactant is a first order reactant. So the integrated rate law for first order can also be expressed as the natural log of A initial divided by A after a period of time equals KT. And that's just a little bit of manipulating of the original equation we had. Now let's talk about half-lives. So let's look at half of an original concentration. So we've got our graph over here on the right-hand side, which we've seen before. Our initial concentration is 0.1000 moles per liter of nitrogen dioxide. And if we want to get down to half the original concentration, we want to go down to the point that's 0.0500. And we're going to notice that that takes 100 seconds. Now, let's look at going to a quarter of our original concentration. So if we start with 0.0500 and we go down to 0.0250, again, we're going to notice that that takes 100 seconds. And if we cut it in half again, that would take 100 seconds as well. So it always takes the same amount of time for a first order reactant to be cut in half over and over again. A half-life of a reaction is the time required for half of that reactant to be decomposed. And we symbolize it with T subscript 1/2. So if we look at the half-life for a first order reactant, and we use that natural log of A initial over A final equals KT, and we know that our time equals whatever our half-life is, that means that if we take our initial concentration and divide it by 2, that will give us our final concentration. So if we plug those values in, we're going to notice that our initial concentrations of A will cancel out. We're going to get the natural log of 2 equals K times our half-life. If we take the natural log of 2 in our calculator, plug that in, and solve for our half-life, we're going to get half-life equals 0.693 divided by K. That means that as long as we know what K is, we can calculate what the half-life of a first-order reactant is. This is the general equation for the half-life of all first-order reactions. For a first-order reaction, half-life does not depend on the concentration that we start with. So let's say we want to look at a second-order rate law. Well, we know that when we look at our differential rate law, we've got rate equals K times the concentration of A to the second, and that's where we're dealing with concentration and rate. But let's say that we're told that the integrated rate law equation is the inverse of the concentration of A after a period of time equals KT plus the inverse of the initial concentration of A. Well, that kind of looks like y equals mx plus b. So if we were to plot the inverse concentration of A after a period of time versus time, we would get a straight line if our reaction is a second order reaction. And that means that our slope equals K. So if time equals our half-life, and we can substitute in A initial divided by 2 for A, we would get our half-life equals 1 divided by K to the initial concentration. And we know that if the initial concentration is raised to the 0 power, it really means 1. So our half-life equals K. It does not change with the concentration. Now, integrated rate law for a 0 order. If we're told that the concentration of A equals negative KT plus the initial concentration of A for a 0 order, again, we've got Y equals mx plus B. What would we plot? We would plot the concentration of A versus time. And if we get a straight line when we plot concentration of A versus time, we're looking at a 0 order reactant. And our slope would be negative K. So our half-life, again, if we were to take the initial concentration of A divided by 2 and plug it into our equation, we would get the half-life for a 0 order reaction to be the initial concentration of A divided by 2K. Now, these occur when a substance needs something special in order for it to occur. Usually if it needs an enzyme like a metal surface in order for the reaction to take place. So in order to sum this all up, if we were to look at a first order reaction, we would take the natural log of the final concentration versus time, and if we get a straight line, that tells us that it's a first order reaction. If we were to take the inverse of the concentration versus time and get a straight line, that would tell us that it's a second order reaction. And if we take the concentration versus time and get a straight line, that'll tell us it's a 0 order reaction.